Okay, so hopefully you've had some time to think about this a little bit, try to determine what types of graphs, connected graphs, would have an Euler path or an Euler circuit. And maybe you found that it has to do with how many edges you have coming out of the different vertices. So in particular, on this graph right here, we had an Euler path but not an Euler circuit. And any Euler path you could come up with would have to start at this bottom vertex and end at the other bottom vertex, or vice versa. So the only paths you had were determined to start and end at those vertices. And so what's special about those vertices? What did we notice about those vertices? Well, suggestively here I've written a definition, which is the degree of the vertices. So the degree of a particular vertex V is just the number of edges connecting V to another vertex. So for this vertex right here, the number of edges coming out of it, that's the degree of that vertex. This vertex has 1, 2, 3 edges coming out of it. So I'm going to label this with its degree, which is 3. Similarly, down here we have 3. And in the center we have 4 edges coming out, so this is degree 4. Up here, 1, 2, 3, 4. This is degree 2. This is degree 4. I'm going to go through and do that with all of my graphs here and see what do they have in common. So in this middle graph, the degrees are 3 all along the outside and 4 in the middle. In this graph here, we have 2 on the outers, then 1, 2, 3, 4 on the inner square, and 4 in the center. And in my last graph, I have 4 here, 3 here. 1, 2, 3, 4. 2, 1, 2, 3, 4, 5. 4 and 2. Oh. I see now that I did mess up here. All right, and I'll show you why in just a second. So the graph that has an Euler circuit, you'll notice all of the degrees are even. And this kind of makes sense because to have an Euler circuit, you need to be able to start at one vertex, visit every edge, and come back to that starting vertex, right? So you need to leave, and then you need to come back in again. Or if you started here, you would need to leave, come back in again, leave, come back in again, right, to start and end at the same vertex. This graph here at the beginning that has an Euler path but not a circuit, most of its vertices had even degree, except for the starting and end point, which had odd degree. And that makes sense because this has degree 3, which means if you were to start here, you would leave out of one of the edges. At some point you would have to come back in through a second edge, and finally you would need to leave again from your third edge. You'd never be able to get back to that point, right? And similarly over here, at some point you'd have to come in, then go back out again, and then come in again, and you wouldn't be able to leave at that point. So those two odd degree vertices means you could start at one, end at the other, and visit every other edge. Now, in this graph that had neither, we had 1, 2, 3, 4. We had 4 odd degree vertices. That's going to be a problem because if we were to start at one of them, you would leave, come back in, leave again, and then you'd never be able to visit this one again. But that's true about this vertex and this vertex and this vertex as well. So if you have more than 2 odd degree vertices, you're not going to be able to find an Euler path. So now I see why I made a mistake in this last one, right? So here we have 1, 2. We have exactly 2 odd degree vertices. So this suggests to us that it's like this first graph here. So maybe I should have just tried to start at one of the odd degree vertices. Maybe I just did it wrong. So I'm going to try it again in pink. Let's go up, over, down, over, let's go to the middle, back to this corner, out again. Then we could try to go up, up, down, and then over to the triangle and back over here again. So it is possible. We just have to start at this odd degree vertex and end at this odd degree vertex. So this does have an Euler path, right? So that was my mistake. And it has an Euler path because it has exactly 2 odd degree vertices. So that's what the Euler path theorem tells us. It tells us that if you're looking at a connected graph, it's going to have an Euler circuit if and only if the degree of every vertex is even, And it's going to have an Euler path without an Euler circuit if there's exactly two vertices of odd degree. This is a great theorem. This is really useful. We can use it for any connected graph to test relatively quickly whether it has an Euler path or an Euler circuit. Okay, and so if we think back to that graph that we drew for the Königsberg problem, it looked like this. Now if I were to go through and find the degree of each vertex, there's 1, 2, 3 edges coming out here, 3 edges coming out here, 1, 2, 3, 4, 5 here, and 3 here. Clearly, the degree of every vertex is not even, so it's not going to have an Euler circuit. And there's more than 2 vertices of odd degree. All 4 of them are odd degree. So since there are more than 2 vertices of odd degree, we can conclude by this Euler path theorem that this graph has no Euler path or circuit. Okay. All right, well, as a follow-up question, what if we only wanted to visit every landmass in Königsberg? Right, what if we wanted to walk around, visit the North Bank and the South Bank in both islands, but we don't necessarily care about crossing every bridge? That one's easy, right? We can do that for sure. Start wherever you like. Maybe go over this first bridge, the second bridge, then here to the second island and back up to the top. So this is a very simple example of a circuit that starts at the top, visits every vertex exactly once, and returns to the starting position. So in a sense, this is like that traveling salesman problem we had on the warm-up, where somebody's trying to visit every city exactly once and return to the starting position. Right? This is a little bit different from an Euler path because we don't care about using every edge. We just want to visit every vertex exactly once. We call such a path a Hamiltonian or a Hamilton path. So it's a walk in a graph such that every vertex is visited exactly once. And a Hamilton circuit is a graph that visits every vertex exactly once but starts and ends on the same vertex. So you can reuse the starting and ending point only. But otherwise you're visiting every edge exactly once. So we'll look at a few examples here. Do these have Hamiltonian paths? Do they have Hamiltonian circuits, or neither? So in the first case, we can see pretty simply that this does have a Hamiltonian circuit. Start wherever you like, let's say at A. Just visit the outer vertices first. But instead of going back to A here, go to F and then back to A. Now that's not the only Hamiltonian circuit, but they'll all look something similar to that, right? Maybe shifted around, visiting F at a different point. So this has a Hamiltonian circuit. And we can describe it by listing the vertices. We went from A to B to C to D to E to F back to A. Okay, in the second graph, do we have a Hamiltonian circuit or Hamiltonian path, or neither? Well, I think I can see that there's going to be a problem here with this center vertex. Because if we wanted to have a Hamiltonian circuit, if we wanted to visit every vertex and return to our starting point, we're going to have to go through this center vertex twice. Because this section of the graph and this section of the graph are only connected through the vertex 3. So whether you started over here or you started over here, if you wanted to get back to your starting position, you would have to pass through 3 twice. So that tells us that it's not going to have a Hamiltonian circuit, but it could still have a path, and indeed it does. Let's say we started at 1, then went to 2, then 7, then 3, then 4, then 6, then 5. That would work. So we would have 1, 2, 7, 3, 4, 6, and 5. Right, and a similar thing happens down here. This is almost the same graph, but with 2 little extra pieces at the end. And so yeah, we could still go from X to Y to Z to U, right? The same basic path, but with these extra points here at the end. Now, what if I were to add 1 extra vertex and edge, say down here? Does this have a Hamiltonian path still? Well, think about it for a second. So it does not, right? So the issue here is if we were to start either at X or at, what should I call this? Call this Q, or at R, you would be able to visit one of the other single degree vertices, right? These all have degree 1, but you wouldn't be able to visit both of them, right? Let's say you started at X. You could start going for your walk, make some choices here, but either you'll eventually hit Q first, or you'll eventually hit R first, and whichever one you hit, you won't be able to leave without repeating the vertex that you came from right before. Okay, so this is an example of a graph that has no Hamiltonian path or circuit. Now remember, with Euler paths or circuit, we had this nice result that said, just look at the degree of every vertex and figure out, does it have all even degrees, or does it have exactly 2 odd degrees, or neither? And it was a real quick way of checking whether a graph had a Euler path or circuit. Unfortunately, for Hamiltonian paths or circuits, it is not that easy. There is no known quick way of figuring out whether a graph has a Hamiltonian path or circuit. So for us, when we're looking at smaller graphs, we just have to guess and check. We have to play around with it until we can convince ourselves that there isn't one, or until we can find one. But for a very, very large graph, this is a difficult problem. Computationally, it's very difficult. It's one of those NP-complete problems if you know anything about computational complexity. So that's a much harder problem to do. So it seems like it should be a little bit easier because you don't have to visit every edge, you only have to visit every vertex, but in fact, turns out it's a computationally very tough problem to solve.